week from Friday. And then you'll be like, well, what do we do the next week? Well, the next week we'll talk about other stuff, like the Big Bang and all that. So finally, it's like a crescendo. If I'm going to get down, talking about our solar system, stars, galaxies, and then the Big Bang. So that's kind of what Unit 5 is. We'll have Monday and Wednesday to knock out some of that stuff. The other thing, no surprise then, is December 8th, which is Friday, when you take your test. That's also the last day that you need to make sure you have all 4 lab write-ups in. Remember that even if you turn in lab write-ups late, they definitely count, so do that. So I have a few things here. The moon is a beautiful target to view this time of year. And then also, this week on Friday, December 1st, is a public viewing at the observatory, and it'll be open 7 to 7:30 for sure, even if it's cloudy. If it's clear, it's going to be like from 7 to 10 sort of thing. Okay, so that's all that. And then I have a little blurb here about your final exam. The way final exams go is you'll have an hour and a half to take your test. And yours, you drew the short straw. So what they do is they take the even hours, which is what this is, because we meet at 10 o'clock, right? So the even hours are on Monday, and the odd hours are, even hours are on Friday, and the odd hours are on the following Monday. Does that make sense? So if you have an 11 o'clock class, that final exam will be Monday. What is that? Monday, Monday the 18th. So any questions about that? So now I did go ahead and up the size of the card that you can bring, 5 by 8 instead of 4 by 6. So it's up to you how you want to do that. And like I've been saying, the majority of questions on your final exam in here will come directly from your unit exams. And just a splattering of questions over the Big Bang and such. And I'll give you a review sheet for that. Okay? Any questions about all that?
You said you will give us a review sheet for the final?
I'll give you a review sheet for Unit 5. And so just like the handful of questions that you haven't seen before. And I don't usually give a review sheet for the final because I figure you already have your unit exams. But I will make a review video and grab a cup of coffee and I'll basically walk through each of your unit exams and I'll narrow it down to the questions. I'll narrow it down so the questions will be on the final for your review. So the way I would watch the review video for the final is I would have my unit exams handy, and then as I did the review video, I would say, oh, she said this one, she said this one, she said this one. I've thought about, well, why don't you just make it a handout? And I'm like, no, that just sounds too, I can't do that. I've done that some semesters, but I'm not going to do this semester. Okay? So I'm hoping every teacher wants well for his or her students, and a lot of times the final, I'm hoping people kick butt on it, honestly. So that's the plan, man. All right. So part of the reason I think we can get through 2 parts today is it's almost like a little picture show again. So I didn't take any of these pictures, by the way. But so for instance, we've been talking about galaxies, our galaxy. What do you think? How many people think that is this face-on or edge-on view of a galaxy? It's a face-on. Now this is a photograph. We've been talking about Messier objects, but actually there's another catalog system out there called the NGC catalog system. Sometimes it's NGC and Messier object. This happens to be object 6946. It's called the fireworks galaxy. Isn't that beautiful? And then we've been talking about if you change, this is in the visible light, okay? By the way, is this, we talked about galaxies. Does this look like an elliptical galaxy or a spiral galaxy? Looks like a spiral, doesn't it? We've been talking about you can look at the same object through different wavelengths. And there it is, changing it up. I think this is taking it up a notch to, I think it's a pretty short wavelength. just different wavelength of the same object. So what's in the center of this object, you think? Black hole. Supermassive. It almost looks a little bit, it almost looks like it could be kind of a barred spiral galaxy if you look at it here, because you can kind of see this looks like major R, major R. I have a little video, I have some videos to show you. This is the Andromeda Galaxy. And actually the Andromeda Galaxy is about the size, a little bit bigger, about a similar size as the Milky Way Galaxy, and it has a couple of companion galaxies. So I think there's this one and this one. They remind me of like a horse. Horse has horse flies, you know, buzzing around. So let's take a look at this little, watch this little video. Technology has been working. Just like 3 minutes long. It's looking, these are photos. This is a famous shot. All right, now I'll leave the lights dim so you can see. What does this look like?
Big Dipper.
It is totally the Big Dipper, exactly. And so what the Hubble Space Telescope did early on in its kind of endeavors to look into outer space and see what it could see was it picked a little place in the Big Dipper where there's no stars. And then what it did was it went ahead and it took, from there it took this picture, so we see stars. And then from there, it took this picture. And this is a famous picture from the Hubble Space Telescope. Those dots are not stars, those are other galaxies. So it just kind of, again, where you take there's nothing, there is definitely something. So I have another video. He does a good job at this too. Probably Friday. So how many galaxies are there in the universe? Sometimes they call it the observable universe. And the amount actually used to be 100 billion galaxies. But then back about a year ago, they took that and they based upon deep sky observations, they took it and said, no, it's times 10. So let's see, 100 billion times 10, that gives you what, a trillion? Okay, so picture a trillion galaxies. Seems like we talked about different types of galaxies, or maybe I'm getting ahead of myself. I'm sorry, I've got science soup, I think, going on. So the Milky Way is a spiral galaxy. It's a specific type of spiral galaxy called a barred spiral. Other types of galaxies are elliptical galaxies, and then we kind of have a miscellaneous category for galaxies called irregulars. Sometimes they're classified other ways, just kind of like how many stars they have. So dwarf galaxies, didn't we have Sagittarius dwarf galaxy that's orbiting the Milky Way galaxy? Okay, so dwarf galaxy just means that it's not very many stars in it, and giant galaxies have a lot of stars. We talked about scientific notation. Which one is bigger, 1 times 10 to the 9th or 1 times 10 to the 12th? Yeah, 1 times 10 to the 12th. Remember the way that goes is you put 12 zeros after that. And that's how many stars are in a giant galaxy. But usually we talk about galaxies being a spiral galaxy, an elliptical galaxy, or an irregular. So this is Edwin Hubble. I think we've talked a little bit about him here and there. So we're going to talk about how he came to classify stars. And again, we're going to add this barred spirals. So with Edwin Hubble, we're going to talk about how you talk about stars, kind of how the shapes of the stars, how you talk about galaxies, kind of how the shapes of the stars make the galaxy. So the galaxy can be spiral, barred spiral, the galaxy can be elliptical, or the galaxy can be irregular. So you kind of see over here, there are little abbreviations. So I don't know if you guys are familiar with like a tuning fork, okay, where you ping it and you go, nee, okay. So this is supposed to be like a tuning fork. You put your hand here and you strike it and it kind of, so this is called Hubble's tuning fork diagram. And what it does is a way to kind of organize the three main types of galaxies. So E stands for elliptical. SB, what does that stand for? Barred spirals. I took it up on you. Barred spirals, and what does S stand for? Spirals, yep. So we have spirals, barred spirals, and ellipticals. Now, out there is a thought that, well, maybe they can kind of, the way the stars are organized in the galaxy can kind of morph from one type of galaxy to another. That's definitely a possibility. So with our ellipticals, okay, let's find the ellipticals, right? So we kind of have subcategories of our E stands for ellipticals. How would you describe the shape of E7 versus E0? Egg-shaped, exactly. E7 is much more egg-shaped. We call it eccentric. That term, we talked about that in astronomy before. When we talked about, if this is the sun, and I just think this is so cool, and this is the shape of a planet orbit about the sun, we said it's not circular, it's oval, okay? And this has a certain amount of what we call eccentricity. Okay. So the more egg-shaped it is, the more eccentric it is. Okay, so if it's circular, it's an E0, it becomes more and more elongated in its size. Well, what would you say about the difference? Let's pick on the spirals. What about these spirals? What's the difference between these three spirals? More arms, exactly. More arms, and then sometimes they'll say how they're squished up wound or they're kind of loose wound. Which one looks like it's more loosely wound? The last one, yep, that's what I was after. And you can actually kind of see these are more loosely wound. So the spiral C is more loosely wound. Does that hold true with the barred spirals down here too? Does the SBC look more loosely wound? I think so too. Yep, good. So we kind of have these subcategories. And it's hard to kind of make it out, but let's pick on the spirals again, SA and SC. Which one looks like it has a bigger nuclear bulge? These two. Yeah, the first one. And it might be hard to tell. But if something's tightly wound, not only is it tightly wound, the arms are tightly wound for the spiral galaxy, but it's going to have a thick nuclear bulge. That's true. That's how that works. Okay, is the same true down here? Tightly wound, thicker bulge. So the A for the spiral, whether it's a spiral or a barred spiral, means that it's tightly wound, thick bulge. By the way, and I still didn't bring my a paper plate in here, but if this is our galaxy, okay, we're seeing it face on here, okay, but what about we've seen edge on? And so what scientists can do, and it comes in very handy, is if you see it edge on, you get a sense at least for kind of the nuclear bulge part. And so if it's a thick nuclear bulge, you're like, hey, dude, I think that's an SA or an SBA. If it's a thin nuclear bulge, you're like, hey, I can't see it face on, but I bet it's got nice, widely spaced arms, and I bet that's an SC or SBC. So that's kind of how that works. We infer a lot of things because we can't visit these places. So this is Messier object number 100. Beautiful. And I've got it in two different wavelengths. This looks like a normal spiral. Oh, This is two different wavelengths. Does this look like a different galaxy? Yes, it's a different galaxy. So which one do we see, A or B, that is edge on? B, yep, we're seeing B edge on. Yep. And you can kind of, I told you, you can see the little bulge part there. Okay, two different galaxies again. This one is unbarred, and this one is barred. See, it's just like a beautiful picture show. So this would be S, and this would be SB. Now on the test, I'm not going to ask you, is it SBA, B, or C, or is it, but this kind of looks pretty loose. I'm kind of thinking SC maybe. It's pretty. So this is a close-up of the, oops, sorry. Yeah, these are close-ups. This one's a close-up of this one. Remember NGC, hopefully, like if you're getting into the astronomy lingo, that's the new general catalog. That just means it's kind of like not Messier, but it's NGC, new general catalog object. Beautiful. So one of the things we kind of take for granted is a lot of these galaxies, and this one too, you see kind of you see the stars, and these would be the OB type stars, those bright ones, right? But can you kind of see maybe some dust regions? Yeah. And if there are dust regions, those are where new star formations can occur. If you see a galaxy that has like no dust, you're like, dude, I think it's just kind of petering out over time. Not a whole lot of new star formation. So switching gears, does this look like a spiral? No. I haven't done this, but maybe we can like do like a little slideshow of, is this a spiral? This is an elliptical galaxy. Okay. Elliptical galaxies oftentimes are humongous, thus the word giant. Okay. This elliptical galaxy there, another elliptical galaxy. So I mentioned dust in those spiral galaxies that we see, the photos of the dust in the spiral galaxies. There's not a whole lot of dust in elliptical galaxies. So they are kind of done with their star formation process in general. Did we talk about population 1, population 2 stars? No, we did not. Okay. Well, I'm not gonna worry about it too much. It was on the homework though? Okay. Well, the way it works, and I hate things that are backwards in science, and it happens all the time. But let's see, population. So population 2 are the grandparents. Really? Population 2, these are old stars. And population 1 are the next generation. These would be newer stars. So we can substitute the word population 2 for old stars. Most stars in elliptical galaxies are population 2, low mass, long-lived. That's consistent with what we've been talking about earlier in this course. Yeah. Actually, there are population 3 stars too that are really born at the time of the Big Bang sort of thing. So we have elliptical galaxies that are giant and elliptical galaxies that are dwarf. Again, giant meaning there's lots of stars, dwarf means there's not many stars. So here's an example of some giant elliptical galaxies. They're just not as pretty as spiral galaxies. And to me, does this look like a globular cluster to you? It totally does to me. But because of its distance, that's not a globular cluster within the Milky Way. Globular clusters and open clusters are all associated with our galaxy. This is a set of distant stars and it's its own galaxy. It's a dwarf elliptical galaxy. Weird. Weird, weird, weird. Again, you might say, well, that looks like a globular cluster, but that is actually way outside of our galaxy. So that's an elliptical galaxy. Down here, does this look like the tuning fork diagram again? You put your hand here, and this is the prongs that you hit. So we have our ellipticals. The 0 means kind of how eccentric, or in this case, circular it is, to E7, elongated. We have our spirals, and we have our barred spirals. And we have our irregulars. So to me, irregulars are just kind of like miscellaneous. We're going to talk probably on Friday about galaxies. Sometimes they interact. Well, heck, Milky Way galaxy and Andromeda galaxy are going to on a collision course. As they interact, they get kind of messy. Okay, and the irregular to me looks like it's been hit by a Mack truck. So this is actually, this object might sound familiar. This is the Large Magellanic Cloud, Small Magellanic Cloud, and it's the one I want to go down to Australia and see. Speaking of, here is, I think I showed you that the other day. Here's the Milky Way, and this is a dome with a telescope. And these are the Large and the Small Magellanic Clouds. So these are galaxies. You can't see them in our hemisphere. We get the Andromeda. They're there again. All right. This might kind of remind you of the image we saw a little bit ago with the Big Dipper kind of zooming in. So those lights are not stars. Those lights are from collections of stars, galaxies, far, far away. Okay. Told you to go fast. So let's see what we got for the next one. You're like, no. I'm like, yes. So we're kind of, again, stepping out. So we're taking those galaxies, and I think I mentioned this the other day, that the galaxies themselves are not just randomly throughout the universe. And we'll talk a little more about this in Unit 5. But they tend to be grouped, and there's two types of groups, okay? So the smallest group is called a cluster of galaxies, okay? So, gravity actually holds the clusters of galaxies together. The Milky Way is a member of a cluster called, don't blame me, called the local group. So it's like the Milky Way's cluster is a group. It's called the local group. Like, it couldn't be any more creative than that. I always think of like, what was that? Where it was a bar and where everybody knows your name.
Cheers.
Thank you. Cheers. I always think of Cheers. Like, so all the people who goes to Cheers would be like different galaxies. I don't know. But anyway, okay. So the Milky Way is a part of the cluster called the local group. Really? Why couldn't they call it the local cluster? This is a picture not of our cluster, but of another cluster of galaxies called the Fornax cluster. To kind of put things in perspective, you're looking at 60 million light years from our solar system. So how far away did I say Andromeda was? Million light years? 2.6. I heard 2.6, 2.5, 2.2. So yeah, about 2 million light years away. Yep. But you'll be happy to know that Andromeda goes to Cheers. So Andromeda is a member of our group. No surprise there. This is the local group, and I looked at this at home and I was like, man, that hurts my head. But the dots represent galaxies. So this is our neck of the woods. And of course, down here we see the different types of galaxies that are color-coded. So we kind of had the poor and, was it poor and rich? Poor and giant before. Now we have the poor and rich. And all that means is that a galaxy cluster that is poor, what do you think that means? They don't have very many galaxies in them, right? Their team didn't have very many players. But a rich galaxy cluster means there's lots of galaxies that are gravitationally hanging out. And, oh, I didn't realize this. Check this out. The local group, that's us. We are a port cluster. Go figure. All right. So when we're talking about clusters, think of them as clusters, like each of these is a galaxy. So kind of picture that as clusters are, these are galaxies of stars that are hanging out. Okay. So we can have regular clusters or irregular clusters. Regular clusters, we're going to see some pictures of them. If you were to kind of stand back, those galaxies are kind of spherically distributed. Okay. Irregular ones are kind of wonky. So this is an example of a regular cluster, and I sure wouldn't ask you this on the test to look at this picture and say, is that a regular cluster? I don't know. Apparently it's generally spherically distributed in space. Now again, we have to switch gears, people. These are not stars, these are galaxies. So that's a regular cluster, this is an irregular cluster. Oh, that's so cool though, that is so cool. You can kind of get a sense for the edge on and kind of the face on and maybe the elliptical galaxies. That's cool. Hercules, does that seem like constellation to you? Yeah, so kind of direction of Hercules. Okay, so clusters is the first step, okay? I'm trying to think. I wouldn't worry too much about that. Beautiful. This is not a figure, this is a photograph. Oh my gosh. This is talking about, instead of clusters, groups. Whoa, check that out. That look like a rich group of galaxies. Actually, this guy, this Abel, and that's another, so we have Messier objects, we have NGC objects, and we have the Abel system, object 1689, so we're going to take a closer look at that. So this is that same rich cluster of galaxies. Let's see if I can get my pen out. And I think we'll even talk more about this before Unit 5. So do you guys see, I see a bunch of yellow here, but if you look real closely, you can kind of see, and they look kind of smeary, you can kind of see these little wispy sort of things, and actually they look like they're kind of wisping in a circle. They're blue. And what the caption will tell you is that those kind of blue wispy things are actually an image that's kind of playing tricks on you. There's nothing there per se, but it's the light being bent by the mass that's brought by that humongous cluster of galaxies. It's called gravitational lensing. This is that same rich cluster, different wavelength. Virgo cluster, you definitely see the giant elliptical galaxy in the center. Same, so these are the same, but it's amazing the things you see when you change wavelengths. So that's Virgo, oh that's cool. Okay. So cluster, hopefully we're thinking like Cheers, cluster, go down to your, and I don't know what's around Cheers, but actually then the clusters are grouped into what's called superclusters. So that'd be like a city block or something of bars. Isn't that funny how bars sometimes they just grow up next to each other? Okay, so superclusters are groups of clusters. You would think somebody could come up with something more original than this, you know, but it gets even better. So this right here, I've heard it kind of analogous to just space. When we talk about the Big Bang, we're going to talk about the creation of the fabric of space-time that Einstein talked about. And as it turns out, space actually needs to have the stars arranged in galaxies, galaxies arranged in clusters, clusters arranged in superclusters, and all of that arrangement kind of goes around these void areas. So it's kind of crazy. So it looks like, it's on the next slide. So this would be where there's nothing, and then these would be where the sponge part is where it would be your clusters or superclusters of stuff. So this is actually a photograph, and those dots are galaxies, to get a sense for how our galaxy is distributed from what we can see. And I don't know if you can kind of see, it just looks kind of like web-like or sponge-like. I saw this blue sponge a minute ago. We have these void areas, kind of these void areas. So this is kind of a return slide. The local group, hopefully if I say local group, you're like, okay, that must be the Milky Way galaxy is a member of other galaxies. And it's a cluster. The local group is a cluster. Oh yeah, here it is. This is the last little bit. To kind of just say, really, can you not come up with a creative name? So the local group is a cluster of galaxies, and our local group cluster is part of the supercluster called the local supercluster. I'm like, seriously, people? I don't know. They ran out of names. It's like when you have too many cats. Oh, sorry. Okay. Well, see, we finished early. So anyway, that's all I got today. And we'll see what tomorrow, or Friday. Don't forget to take your surveys.